Hello, my name is Socrates Metαξάς, and I'm the manager of the water board of Limassol in Cyprus. In this presentation, I will present the progress of the innovative application of digital twins in our organization. Cyprus is the third biggest island in the Mediterranean Sea, located in the Eastern Mediterranean. Unfortunately, it is faced with cyclical periods of drought and high costs of water production, mainly due to desalination and the rising energy costs. Our organization is the second largest water utility in Cyprus, supplying water mainly to the urban area of Greater Limassol. We supply water to 110,000 consumers, which corresponds to approximately 180,000 people over a network of 1,300 kilometers of pipes. We are also faced with a lot of challenges. Our non-revenue water is currently at 23%, and in the next few years, our organization will expand rapidly to become a district water provider. In the past years, we invested in new technologies such as sensors, smart metering, and GIS. However, these technologies on their own are not a panacea. We need to have tools that help us make the operation of our system more efficient based on intelligent data analysis. Every day in our organization, we need to deal with operating issues such as which consumers will be affected if we close a certain valve for repairs? How will the pressure in the network change when we connect to DMAs? Where is the possible source of a water quality problem? How to set the pressure reducing valves to minimize leaks? Which type of pipes has the highest risk of failure? Where to install new water quality and pressure sensors? What will happen to the flow, pressure, and quality if new development occurs in a remote area? I'm sure that these questions are common to most utilities represented at this IWA Congress. Taking into account the existing challenges and opportunities, we have collaborated with the GEOS Center of Excellence, a research center at the University of Cyprus, and FIVI Innovations, an SME, to design a digital twin for our organization. A digital twin is comprised of three main elements. First, a physical system that is monitored using smart sensors. Second, a digital model which replicates the physical system in real time. And third, applications that use the digital twin and enable management to make decisions and apply them to the physical system. In the figure, you can see the architecture of our digital twin system and the steps we took to design it. As a first step, we installed pressure sensors at optimal locations in our DMAs. Next, we integrated GIS data, hydraulic models, and SCADA data from the field sensors to create an accurate mathematical model of the system. This is achieved using a real-time state estimation module that calculates the states of the system, such as flow in pipes and pressure at nodes in locations with no sensors. Essentially, we create thousands of virtual sensors. The outcome is an accurate digital model close to the physical system that can be used by smart applications to answer management questions like the ones mentioned in the previous slides. The operator or manager can then apply these results to the physical system. The final objective is to facilitate reliable decision-making while improving efficiency. This digital twin architecture could be enhanced when automated meter reading infrastructure is installed and fully operational. The proposed digital twin was demonstrated within the WaterAnalytics project funded by the Research and Innovation Foundation of Cyprus. The pilot area covers 3 DMAs with pipes of 45 kilometers in length. We installed 30 pressure sensors, 5 water quality sensors, and 3 flow sensors, as well as 1 controllable pressure reduction valve at the entry in one of the 3 DMAs. All data received were integrated in the WaterAnalytics Digital Twin, which generated live hydraulic models. These models were calibrated using the real-time state estimation module, which utilizes the measurements retrieved from the pressure sensors. These live calibrated models are then used to answer what-if scenarios using research-based methods. An example of a what-if scenario is how to regulate pressure in order to reduce leakages. We examined the effectiveness of a pressure optimization technique that regulates PRV settings to minimize the pressure within a network, while of course satisfying minimum pressure requirements. This application was tested on the digital model of one specific DMA, namely DMA 131, an area with 3,500 consumers. A reduction of the inlet pressure from approximately 50 meters to 40 meters resulted in a reduction of the minimum night flow of 3 to 5 cubic meters per hour. To further assess the effectiveness of this method, the digital twin is used to calculate key performance indicators which correspond to the operation of just one DMA for 1 year. So, for this specific DMA for 1 year, the savings in water losses were more than 5,000 cubic meters. The cost of the water saved more than 4,000 euros, and the reduction of CO2 emissions by more than 700 kilograms of CO2. After evaluating the results of this method using the digital twin, the proposed method was applied in the physical system. Using the controllable pressure reduction valve, which was installed at DMA 131, we reduced the pressure to the same levels as with the digital model, from approximately 50 to 40 meters. This resulted in a reduction of the minimum night flow by 5 to 10 cubic meters per hour, which is close to what the model predicted. The figure shows the real inlet pressure and flow measurements of DMA 131 retrieved from the SCADA system at the time of the pressure reduction application, shown by the blue vertical line. Another typical question is where to install water quality sensors. In general, it is difficult to install a large amount of these sensors everywhere due to their high cost. The application uses the calibrated hydraulic models and through a scientific optimization-based approach, finds the best location to install sensors while trying to detect the contamination as quickly as possible and to minimize the contaminated water consumption volume. The results are then visualized on a map, and we see here with just one sensor available, the case 1 map, with 2 sensors available, the case 2 map, with 3 sensors available, the case 3 map, and similarly with 4 sensors available, the case for map. And here we see the geographic coordinates, the nodes where we installed the 4 sensors. To conclude, in this work, we developed and demonstrated a digital twin that is easy to use by technical operators and can examine various what-if scenarios. It can be used for systems without smart meters using just pressure sensors. It integrates a state estimation module, which is an important step for accurate digital twins. We believe that this project was a successful collaboration between the public sector, academia, and industry. Our next steps include the full deployment of the WaterAnalytics Digital Twin at the Limassol Smart Water Network Living Lab, integrate with 110,000 smart meters, 200 pressure sensors, and 80 quality sensors. We are open to support other utilities in adopting this digital twin technology. I wish to thank you for your attention. For any questions, information, and possible collaborations, you may find me at the email shown at these slides. Thanks a lot.